Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure today to introduce Chris Ostrowski. My best. I'm not even going to try the first name. Who is graduating from Cornell this year, one of Ken Berman's students, and has done some very interesting work on programming abstractions, programming models for large-scale distributed systems. And he'll tell us about this work today.
Thank you. And I am very grateful to be here and to present to you. Hope that you'll enjoy my work. Okay. So let me start by introducing the concept of a paradigm-agnostic web. This has served as a practical motivation for my research. Today's web technologies are strongly rooted in the client-server paradigm. So we assume that content and services always reside on servers in the data centers. The clients don't participate in delivering the service or storing the content, and mostly just don't talk to each other, only talk to the server. In a paradigm-agnostic web, we would have much more architectural flexibility. So, for example, the content could be stored only in the clients. Those currently involved in accessing it could form a replicated state machine. Whenever one of them makes a change, that would be disseminated in a peer-to-peer fashion using reliable multicast or similar technique. New clients could synchronize with the existing ones. So in the extreme case, the clients might never actually need to talk to the server anymore. And of course, in practice, we would be most interested in various hybrid techniques where you have elements of peer-to-peer and client-server interactions, where the server could be used to discover the clients, to self-organize, persist the content when the last client is about to depart, and so on. Now, to show you that this idea makes practical sense, I developed a platform. So here's a little demo of the platform in action. On the left, you see a user interactively composing a shared document. All the links she's dragging are just links to live web content. Now, on the right, the user opened a second replica of it. As you can see, whatever you do on one replica is instantly propagated to the other one. And you could have multiple such replicas here, both on the same machine, but they could be in different places over the network and synchronized across the network using distributed protocols. So this is a little bit reminiscent of Google Wave or Chrome OS in the sense that all the data that you see exists in the network. And the main difference is that this is a paradigm-agnostic document. So any type, any part of it could use any type of a distributed protocol as a way of sharing state, including peer-to-peer techniques. And here's another example, this time a three-dimensional shared document. And again, everything that the user is dragging is connected to live data source. For example, those buildings are connected to multicast streams that carry color values. And those are used to paint the building's roofs. And the planes are connected to streams of coordinates that could come, say, from GPS devices and real airplanes. So you'd have a little augmented reality system. And those multicast streams are themselves draggable. For example, in a second, you'll see when a user opens a plane, extracts a multicast stream out of it, and then drags and drops it into the window to connect it to cameras, so you can have various sorts of functionalities like this. Now, in practice, the choice of the distributed protocol will usually depend on the type of content. So, for example, and the list of objects in a shared document could be stored in a web service, but then the contents of this little chat window could be stored using replication techniques. Likewise, the list of objects in space could be stored using replication, but maybe then the coordinates of an individual airplane would be delivered using a gossip protocol. So in an application, in a paradigm-agnostic application, in general, any element could use whatever communication and storage architecture best matches the workload patterns, the quality of service requirements, or the characteristic of the environment over which this particular component was replicated. Now, there are two types of benefits and challenges in pursuing this idea. On one hand, by incorporating peer-to-peer techniques into existing applications, we could potentially improve scalability, latency, We might even lower the resource footprint at the data center because the clients could do some work for us. And then, of course, the challenge is to maintain predictable quality of service and security in a peer-to-peer setting, which can be harder. On the other hand, if we manage to somehow seamlessly incorporate all sorts of distributed protocols into the modern web development toolchain, then we can reap the productivity benefits that these modern tools provide in building arbitrary types of distributed systems, not only those that are based on the client-server paradigm. And so what I'm personally most interested in and what I'd like to focus on in this talk is how we can generalize the existing web development tools, software engineering practices, languages, to help us manage complexity in this more general distributed systems setting. I think the main source of complexity in distributed systems is what I call an endpoint-centric perspective. Today, we generally describe behavior of systems in terms of what happens at an individual node, a single communication endpoint, which we often model as a finite automata in terms of low-level primitives such as receive a message, send a message, transition state, file timeout, and so on. If we program at this level, most systems are very hard to express, even if we have a cutting-edge programming language such as Overlog. As you see in this example, for Paxos, you would need 40 rules like the one shown at the bottom. And that's true even for a version of a protocol that's described in the research paper. And of course, then in the real world, we have much more complexity to worry about. The internet is heterogeneous. Consider this example set of 8 users and 2 servers. And suppose they're all involved in either accessing or replicating, storing the content of that little chat window. And then suppose that they want to coordinate their updates using reliable multicast. Now, perhaps these 4 clients are on a campus network, so they can locally take advantage of IP multicast. Those 3 guys are on a wireless network, so they could ideally use forward error correction. And those guys on the right would be in a data center, so maybe they have some super fast enterprise message bus available. And across these 3 domains, the peer-to-peer overlay would be the most efficient communication architecture. Now, it's clear that in order to make the best use of resources in real systems, we should be able to build those systems in a modular fashion by combining protocols, different kinds of protocols deployed in different regions into a single unified substrate. And doing this in the endpoint-centric perspective is more difficult because when you look at this picture, it is obviously evident that there are some hierarchical relationships, and those become obscured once we translate everything into C++. So now the question begins, so how should we structure our language to make it easier to work with such relationships? Well, if you look at this picture, it is clear that these 3 regions in the middle, blue, red, and green, are in some sense components. Every region recursively delegates some work to the regions contained in it. The protocol that runs in each region is like the code that implements that region. So you could think of it almost as like a recursive function calls or a recursive data structure, except that these regions are not objects or functions in a formal sense in any particular language. Intuitively, it is also clear that we could replace a protocol that runs in each region, for example, take advantage of IP multicast in the green region, without necessarily changing the semantics of the entire system. And that would be intuitively a little bit like replacing member field in a data structure with some other object that implements the same interface in a slightly different but equivalent manner. And so we would like to be able to take advantage of those intuitions. And in the next section, I'm going to describe a programming model that was inspired by this idea. Sure.
What do you mean by recursion?
In the sense that any region has some work to do, for example, recover from losses. And if you look at this structure, as any region contained in it has essentially the same work to do. So it's, in a sense, it's of the same type. The same type of work is being done. And that can continue recursively. In my model, an object is formally defined as a set of software components distributed across the network. The components that make up an object are called replicas. So Here we have an example with 3 users accessing the shared document. And we have 2 objects. Replicas of the application object are instances of the user interface widget that displays the document on the screen. And then the replicas of the multicast object are instances of reliable multicast protocol stack that is used to disseminate the updates between the clients. And pairs of replicas located on the same machine communicate by method calls and callbacks, which we can model abstractly as events. And by the way, an object could have infinitely many replicas. Formally, it contains all the replicas that exist right now, existed in the past, or will exist in the future. Now let me pull the 2 objects to the sides. Now all the events they exchange are shown as green arrows in the middle. Formally, the set of all events of the same type flowing between a pair of objects is what I call a distributed data flow, or flow for short. So for example, the send flow will be the set of all multicast requests generated by the application, the set of all those green arrows surrounded by the yellow potato. And just like objects, such flows could span over infinite time and infinitely many locations, since formally flow contains all the events that are occurring right now, occurred in the past, or will occur sometime later. Now, with these definitions, we can represent the architecture of our system in a way that resembles a Petri net. This new flow, receive at the bottom, is the set of all callbacks that carry the received updates from the multicast layer into the application. And now we can think of the multicast object as a sort of a function that transforms one input argument, the same flow, into one output argument, the receive flow. Almost like in Java, except that whereas in Java, we would transform integers, booleans, and other primitive values. So here we are transforming the entire distributed flows. And here's a possible signature for the multicast object in my language. It resembles a function definition with the input flows listed in parentheses and the output flows following a colon. The name of a flow is always preceded by type, just like in C. The type of the flow determines the types of values that are carried in each event. So here we assume that the updates will be represented as strings, so that's the type. The type also contains optional behavioral constraints. So for example, receive was declared to be consistent and fresh. Those behavioral constraints tell us something about the spatial and temporal patterns of events in the flow. And to give you a taste of what these may mean, formally we model each event as a quadrupole, location and time where it occurs, version k and value v. For example, in a receive flow, the version might be the sequence number of the received update, and then the value would be the payload, the content of that update. With this formalism now, we can define different behavioral constraints by relating pairs of events that occur in different times and places. For example, I say that a flow is consistent if any pair of events, no matter where or when they occur, if they have the same version, they also have the same value. It makes sense that the receive flow would be consistent, since you wouldn't want 2 completely different updates to be delivered with the same sequence number. In general, the consistent flows in my model will usually carry information about various decisions that have been somehow made in a coordinated manner in the protocol. A special kind of a consistent flow is a monotonic flow, where a larger version implies a larger value. And as you will see later, monotonic flows carry information about decisions that have been somehow remembered by the system persistently. And I will explain what that means later. And more of such constraints are defined in the paper. If time permits, I will show you how we can use this to drive compiler optimizations. Are there any questions at this point? I'm sorry?
What is fresh?
Oh, fresh. It basically means that nobody is lagging behind. So if somewhere in the network a certain version of an event with a certain version appeared, then on every correct node, at least that or higher version will also appear. Now, meanwhile, let me explain how we can model larger systems using this approach. So here's an extended version of our previous example. Suppose that a multicast protocol now has a modular structure. So first it disseminates updates using some unreliable method, and that's taken care of by component U, and then does loss recovery, that's component C. I can model the groups of these components as two new objects, violet and green. Likewise, suppose that the replicas of the loss recovery object self-organize using a membership information that's obtained from some cloud service. Then we can identify the protocol for contacting that service and model it as this new orange object in the middle, and so on. And we end up with this sort of extended diagram in which different objects span across different sets of locations. And from now on, I'm going to always represent flows as those yellow sandwiches here. Now, if you look at this diagram, you see that flows in this model serve as typed contracts that decouple objects from one another, very much in the same way as typed interfaces decouple web services in an ordinary workflow. Now, this diagram is maybe useful as a way of modeling systems, but it's not an executable program. What I'm going to do now is I can zoom in on portions of this diagram and then recursively decompose each object into smaller parts until the moment where everything in the diagram is expressed in terms of a handful of basic building blocks. So let me zoom in on loss recovery as an example. Now, my contract says that there's a single input flow carrying into the object information about what updates have been received at the different nodes across the system. And my job is to generate forwarding decisions and decide when updates are stable everywhere. I'm going to model each update. I'm going to model each event as carrying a set value, a set of integers, where each integer represents a sequence number of one update. So here in those two events, suppose those two events appear in the arrived flow. The replica of loss recovery on machine Bob just learns that Bob has all the updates from 1 to 2 and from 4 to 7. And the replica on machine Alice has learned that Alice has all the updates from 1 to 3 and 8. Now, and by the way, I'm going to always assume that here and in all other parts of the model, whenever a flow is carrying certain type of information, every event carries complete information. So here, every event will contain the identifiers of all the updates that have ever been received in the past, even if they have already been reported once. Doing this little trick makes it much easier for me to model about progress in the system. I can always express progress as monotonicity, as I will explain later. And this is something that can be very easily taken care of by the compiler, so the user doesn't have to bother about it. OK, so we have those set values in the object now on different replicas. And one of the things that, as I mentioned, loss recovery have to do is tell us when updates are stable across the system so we can do the cleanup. Well, having that information, we can just calculate set intersection. The result will be 1 and 2, and that's what should appear as events in the stable flow. So this is very simple, and it's actually one of the building blocks in the model. An aggregation can have different flavors, like the particular kind used here is characterized by those blue keywords at the bottom, and I will explain those in a minute. Meanwhile, let me just give you some intuition how we can model other parts of this object. So suppose that we aggregate events in the arrived flow using a set union operator. Well, that will produce the set of all updates that are present anywhere in the system, because we'll just add up all the sets of identifiers that everyone has reported. And now, by subtracting those values from values in the arrived flow, we can calculate the flow of information about which updates are missing on which nodes. And so you see how, in this fashion, we can successively build up, by applying those set operations, we can build up a flow of forwarding requests that can be carried out of the object. And now, if you compare this representation of a distributed protocol with the code in C++ or even rules in Overlog, and clearly this is a much higher level, we can clearly see what kinds of information are involved in the protocol, how the protocol makes decisions. Those relationships are presented in a way without cluttering them with various lower-level details, communication details and other such. At the same time, this is a constructive representation because we have a very small number of those building blocks. We know how to implement them. And this is also something we can formally reason about. I'm not going to present too many formulas in this talk, but most of it is described in the paper. Aggregation is a transformation on flows where for every event in the output flow beta shown on the right here, we have some finite set of events in the input flow alpha that happened earlier, and such that the value here in this event is an aggregate of the values in those events. So that's simple. Now, the different kinds of aggregations, the different physical protocols, the different formal flavors of aggregation will, of course, differ in the way we select those input events. For the kinds of aggregation that we care about, we can characterize this selection in a slightly more explicit way. And without going too much into detail, we can characterize aggregation by two families of functions, memberships and selectors. Intuitively, for every event in the output flow, memberships first tell us what are the locations that participated in the aggregation from which this event was generated, what are the nodes that have communicated to generate that event. And then for each of those locations, the selectors tell us what was the version of the event that this particular location has contributed. And since in this model, a location and a version determines the value uniquely, that's all the information I need to express, completely write out all the values in the output flow in terms of the values in the input flow. That's shown by the formula at the top. And the details are not that important. But I want to point out is now, having such formal characterization, I can distinguish different flavors of aggregation by placing various constraints on the memberships and selectors. So for example, I say that an aggregation is in order if all the selectors are monotonic, which intuitively basically just means that whenever I aggregate, I'm using the latest information I've got. Or a complete aggregation will be one in which once a non-faulty node makes it into the membership, it will be in every membership with a higher version. Right? That basically intuitively means nobody's left out without a good reason, and so on. Now, with all those formal definitions, I can now reason about the object flow diagrams, about the system behaviors abstractly, without having to worry about the specifics of a particular protocol. I only need to know what flavor of aggregation a given protocol implements to know how it transforms my flows. And theorems like the one shown at the bottom, there are more such in the paper, basically become rules of type checking. So for example, here, if I know that the input flow is of a certain type, I think this weakly monotonic, and the aggregation is guarded, coordinated, and so on, then I know that the output flow is strongly monotonic, right? So I can apply such theorem as a type checking rule to every edge in my object flow diagram, and by doing so, for all the edges, I can convince myself that the system has the sort of behavior I wanted it to have.
So can we ask you a question? So you can apply this kind of rule to the abstract diagrams
right.
that you had previously, but can you infer these properties from a code that would implement, or could you check that the code actually implemented these properties correctly?
Presumably, you could, in future, do that, infer the properties from the code. I don't know how to do it, but I envision it might. It might require some assistance, maybe annotations in the language or special language features to infer those, but I believe that's possible. OK, now, aggregation is a basic building block in many systems. For example, in MapReduce, data parallel frameworks such as DryadLink, and so on. The kind of aggregation that we need here to construct distributed protocols as a building block is a little different. In particular, one especially important kind of aggregation that's used to express almost anything has the notion of memory. And let me explain what it means using an example. So suppose we have 3 replicas of an aggregation object, consuming those values shown at the bottom, and calculating set intersection and producing value at the top, transforming flow arrived into flow stable, as I described before. Now suppose that the machine on which the value was calculated suddenly crashes. Meanwhile, some other node arrives and joins the system, participates in the very next aggregation. And suppose that this node is totally new. It hasn't caught up with everyone else, hasn't received any updates. So the value that appears locally in the arrived flow reported by the other layer in the system is an empty set, no updates. And that, of course, causes the result of the aggregation to also be empty. And then we have a problem, because previously we reported that updates 2 and 3 are stable. Maybe some other part of the system already acted upon that information. And now we changed our mind. But if something is stable, it should have remained stable forever. Right? So this is unacceptable. In order to use an aggregation object in our system, and the object needs to somehow remember what it has reported in the past and make sure that whatever it reports in future is consistent with that past report. Now, if you recall, every event in this model has a version. And if a flow is monotonic, a higher version implies a larger value. So that would be set inclusion in this case. So if I know that the result of the newer aggregation after the crash is tagged with a higher version number, and if I know that my protocol produces a monotonic flow, then I know that this problem will not occur. And the theorems like the one I showed you in one of the previous slides actually can help us to prove that certain flows are monotonic and help us understand exactly how we need to construct our aggregation protocols to produce the desired behavior. And this particular kind of aggregation, the monotonic aggregation, is very easy to implement if you have access to a membership service, which was the case in our previous example, if you remember. Now, one aspect of monotonic aggregation that's quite unique and that I want to elaborate on is the possibility of implementing it in a scalable manner on a heterogeneous system without needing a single global membership service. Consider this example group of 10 nodes across 3 administrative domains. I'm going to align them at the top there. And in the middle, I'm going to draw the components that run on them. So every vertical segment of the screen will be the set of components running on one of the nodes. Now, suppose that on a campus, there is an aggregation object. Every node on the campus network has a replica of it. And those replicas self-organize into a group using a local membership service that's deployed to manage the campus. I'm going to assume that on every administrative domain, bigger or smaller, there's one such membership service deployed to manage it, and that there's some mechanism in place that allows a node to automatically find what is the locally deployed service and register with it. Now, consider a part of the arrived flow confined to the campus. This is shown here. This flow is transformed by the campus by the campus aggregation object to produce that flow at the top, information about which updates are stable across the campus. And so we have one input flow, one output flow, one object, and no matter how many times the nodes in the campus crash and recover, we still have a single output flow with a single property, monotonic. Now, suppose the same happens in the other 2 domains, on the airport and in the cloud. So in each domain, nodes will locally self-organize using a local membership service, this one and this one, and form a single aggregation object, which will transform some part of the arrived flow to produce a single output flow of information about what is stable across that domain. And so we have 3 stable flows. And now further, suppose that in every domain, a selected leader node, and that leader might change actually dynamically, it doesn't really matter. A selected leader passes this local information further to a higher level in our infrastructure. So we're going to have such a hierarchical implementation. Those 3 leaders then use a membership service deployed for a wide area network to self-organize into a single yellow object, aggregation object, of the same flavor. By the way, here, each of those 4 objects can now be implemented in a completely different manner using whatever mechanisms are the most appropriate for that particular domain. The only thing I need to assume is that all these aggregations are of the same flavor. So this is the part where we can already introduce heterogeneity into the architecture. And I'm going to refer to every such heterogeneous aggregations hierarchy as an aggregation network. So now, the input flow for the yellow object is the union of the output flows from all the domains below it. And the output flow is information about what is stable across the entire system. Now, using our approach, I can model this entire dynamically reconfiguring hierarchy using a single object flow diagram, in which, as I explained before, and every input flow is the union of the output flows of aggregations below it. And this diagram is very simple. We have a very small system with only 3 domains now. In general, of course, nodes might fail, reboot. New nodes might arrive. Those new nodes might reside in different administrative domains. So the entire new domains might be introduced to this hierarchy. New levels in the hierarchy might be created, and so on. We can still model such a dynamic, arbitrarily nested hierarchy as an object flow diagram, except that this diagram may be infinite. So it may be infinitely tall, and every element in it can have infinitely many children. And those infinitely many children come from the fact that if new nodes keep arriving from new domains and those are appended in the hierarchy, become part of the structure, then that's where the infinite children comes from. And fortunately, I have proved that any such hierarchy constructed out of monotonic aggregations, potentially different protocols, each of which implements monotonic aggregation, in fact behaves as if it were a single global system-wide monotonic aggregation. And so that's good news, because that means that whenever I need to use monotonic aggregation as a building block in my system, as was the case in, for example, loss recovery protocol you've seen earlier, I can always implement that building block in a hierarchical manner using the approach I just outlined as a hierarchical aggregation network. And it turns out that monotonic aggregation, the same building block you've seen, can be used to express many commonly used protocols, such as distributed locking, leader election, various forms of agreement. It seems that we should also be able to model the classical consensus protocol in this fashion, although we still have to work out some details. So potentially for a very wide range of systems, we can implement them in a scalable and heterogeneous manner by following this approach. Yeah?
So it seems like if you had a cloud, let's say, that didn't want to be involved in all the peer-to-peer transfer,
right,
all the high bandwidth streams, whatever, but was just sitting there to do just ordering, basically,
right,
hashes, and maybe to decide what is the wouldn't that make this problem a lot simpler? Because it would determine the order, it would determine what is stable.
Right, you could use that. So you could use cloud only to help you manage membership, or you could use cloud for ordering. Of course, then implementation of each aggregation object would be much simpler. But still,
so why wouldn't you want to do that?
Well, potentially, sometimes you may want to do work at the client side, right? Because maybe, I don't know, some group of clients is on a network where they can really very efficiently talk to each other, and it is just faster for you to organize this communication in a peer-to-peer fashion, coordination in a peer-to-peer fashion.
So can you give me an example of an application where you couldn't wait for the server to timestamp as
Well, one classical application where people use distributed protocols is, for example, the Wall Street. So in those applications, you might want to do that. There are also many scenarios. Actually, our funding comes, part of it, from the Air Force. And there are a lot of scenarios in which just most of the time you don't have uplink connectivity to the data center, and you still want to run your collaboration. In fact, they want to have web applications without having the web, right? And so these are the types of applications where you're actually forced to use peer-to-peer approaches in architectures like this. Okay, now, just to conclude this section, let me show you a little bit of a performance result. This is a simulation of a system built using the methods that I described earlier from the model. It's a simulation, but it's realistic. So we have actual point-to-point message exchanges. Nodes form token rings, run those tokens around the ring, do aggregation, and so on. They all independently fail and reboot. After rebooting, they have clean state and have to reinitialize, and so on. The system size varies from 60 to 32,000 nodes. The mean time to reboot is shown on the x-axis. sorry, the mean time to fail. The mean time to reboot is 5 seconds. And we simulate a simple barrier synchronization protocol where we want nodes to enter subsequent phases of processing in a coordinated fashion so that no two nodes are more than one phase apart. And that is expressed as a single monotonic aggregation. And that aggregation is then implemented as an aggregation network, like I described before, in a hierarchical manner with lots of membership services managing the different regions and different layers. And each aggregation object in the hierarchy aggregates 10 times per second. But then, of course, it takes time for the information to surface to the root. And so we measure the route trip time, how fast it takes for the system as a whole to enter the subsequent phases of processing. And that gives us an estimate of the round trip aggregation time that's shown on the y-axis. And so one thing we notice is that the latency within which the system works is logarithmic. As you see, every time we grow by a factor of 8, latency grows by the same amount. And this is consistent with what we would expect theoretically. And the second thing we notice is that this structure is actually quite resistant to churn. It's quite an extreme churn rate where half of the system is reconfiguring at any given time. And we can still work with maybe a 20% performance penalty. And that's because every aggregation object in the hierarchy basically handles its own failures independently. So when a single node fails, that affects on a small part of the system, doesn't have to destabilize the entire network. As would be the case if you used a global membership service across this 32,000 node system, all these failures would cause global membership changes. You could, of course, batch them, but then once you start to batch them, that would increase your response time, so you couldn't handle a failure in a timely fashion, and you couldn't do any work. So there's an improvement. There are more results in the paper, but I don't think I have that much time, so I'm going to.
So this was a graph tree aggregation?
Right, this is a balanced tree. So of course, in reality, you'd have to work hard to build a balanced tree, but that's the part I didn't evaluate in this paper. OK. So here's an example of a partial implementation of the loss recovery object you've seen before. And you will recognize the object signature at the top since I've explained it before. Now for the body, one way to think of it is essentially as a textual representation of this object flow diagram you've seen before, shown below here. For now, please disregard the grayed out statement and just focus on those 3 highlighted assignments. Every occurrence of an arithmetic operator, or everything that looks like a function call in general, is an in-place declaration of an embedded object. So we have 3 such occurrences. We declare 3 embedded objects, 2 of which are aggregations. We can declare internal flows just like we would declare local variables. By the way, the order of the statements doesn't matter in this program because these are not one of statements that run to completion. There's nothing sequential about this program. Basically, these are all just declarations. So implicitly concurrent with respect to one another. And every time we pass some arguments to an operator or consume the result, we declare a flow dependency. So we declare those black arrows in the diagram. Now, notice that we don't need to specify the type of aggregation. Certain things are assumed. Most of these properties are taken for granted unless you specifically say that you don't want them. One of them is implemented by the grayed out statement. I'll talk about it in a minute. And finally, notice that we never talk about membership here. It is implied that in order to implement certain types of operators, for example, monotonic aggregation like the one used here, you either need to use a global membership service to self-organize, or you have to construct the scalable aggregation network like I showed you before, and then you use lots of membership services for that. And anyway, there's no need to burden the programmer with any of this, since the program doesn't really care whether you have some membership in the system as long as all the flows are transformed in the way you want them to. So we consider this an implementation detail that's taken care of by the compiler or even at the time of deployment. Now, just very briefly, what it means to translate such program, compile such program. Basically, you generate an object graph like the one on the right, where the root component is always the replica of the object you're defining. Whenever you have some embedded object, you create a replica of it. Since these are built-in building blocks, just code is pre-generated for you. And the structure of the program determines how events are going to fly around this infrastructure within each replica. I'm not going to go into detail, but basically you can think of production rule systems like those based on the RITI algorithm, where you have graphs of elements, and every time one of them gets updated, that causes other elements to get updated accordingly. OK, now back to our language. Just like in any high-level language, we have a conditional statement, the where clause. The argument here in parentheses is a Boolean flow, any type of a Boolean flow. This time, this one is represented by the highlighted expression. And the way it works is that whenever a true event appears in the Boolean flow at my replica, locally the body of the where clause gets activated. Whenever a false event appears, or when there was no event, the body gets deactivated. So where in a typical language, conditional statements tell us which chunk of the code has executed. It's a binary, yes or no. Here, our conditional statement tells us which subset of replicas is running that code. So in this case, which subset of replicas is doing aggregation? To deactivate a body of code basically means to suspend all the local flow of events. And in case of aggregation, that means that the local replica will not submit its own local values for the aggregation, will abstain from the aggregation, right? So the meaning of this entire statement here is that the only replicas that will vote over which updates are stable are replicas that first know the latest value in the stable flow and have all the updates that are considered stable, right? Which makes sense, since if some node doesn't have the updates that the system considers to be stable, then it can't consider itself to be part of the system, right? It has to abstain from election, from aggregation. So conditional statements like this can be used to model all sorts of join conditions that you have to put the new members through to ensure that they are synchronized with everyone else. OK. Now, for the end, let me show you one complete example, a very simple distributed locking protocol implemented using leader election. We have a single input flow, Boolean flow once. A true value on a given location in that flow means that the particular node wishes to acquire the lock, and a false value means that the node no longer needs the lock. Now, when an event with a true value appears at a replica, this causes this body to be locally activated, which means that the replica of stable elect on that node will get activated, which means that we will participate in aggregation. I'll show you in a second. So once we communicate our intent to acquire the lock, our local unique identifier, this is just a built-in flow, gets submitted into that replica. And once we get elected as a leader, we remain elected as a leader. Again, I'm going to explain it in a second. So once you find out that the leader identifier is same as ours, we can respond to the application that, yes, we've got the lock now, and we know that we will continue to be the lock holder until the moment where we just give up ourselves. And here's the implementation of the scalable election protocol. So we have a single input flow carrying the identifiers of the candidates for election. We elect a leader by just picking the minimum identifier of the candidates and report it back. Now, to ensure that the result of election is stable, as I said that we need to, I'm going to request that if I know what is, I can only participate in election if I know who is the current leader, and my own identifier is not smaller than the one of the leader. If that was the case, if my identifier was smaller and I participated in the election, then I would overthrow the leader. I would become the leader. I would violate this condition that I wanted. So So this little join condition ensures that the new nodes coming to the system will not cause the change of the elected leader until the moment when the leader gives up. And so this is actually a correct protocol. The only problem is that it can lead to starvation, but that can be fixed. I'm not going to go into detail today. OK, I'm going to skip this slide. OK, to conclude this talk, let me say a few words about other works I've done. Essentially, everything I did grew in this way or another from my early work on scalable, reliable multicast here. I've built a system in C# that can deliver data close to network speeds and scale to hundreds of nodes with almost no performance penalty. Actually, that penalty that's observed is due to garbage collection overheads that I can't control. The main challenge in building this system was due to the fact that with hundreds of nodes, all of them basically at their maximum capacity, CPU, UI-wise, and network-wise, it's very easy for any little event anywhere in the system to destabilize the entire system because these events tend to cause cascading problems. Reactive recovery techniques usually cause more timeouts, and those timeouts cause even more timeouts, and so on and so on. And so most of the time I spent profiling carefully, trying to understand the source of these instabilities and preventing them. Another major line of work was working enabling Paradigm-Agnostic Web applications, and that includes the demo you've seen earlier. And that was mostly published in the web services crowd. And finally, I also developed a concurrency abstraction for multicore platforms over there on the top. It combines the benefits of MapReduce and actor model. In a nutshell, the idea is that a single component in my system can automatically decompose itself into multiple replicas. Then those replicas can handle method calls in parallel. And as necessary, it can shrink itself back into a single replica and then become an ordinary actor. And all this is happening in a way that's completely transparent to the user calling into the object. And it's almost transparent to the programmer. The programmer has to implement some method to split a replica in two and to merge two replicas back. But all the coordination, all the synchronization, scheduling, and so on is taken care of by the platform. And so an object implemented this way can actually continue to go through such phases where it behaves like an ordinary actor and phases where it gets replicated, can shrink and grow in a manner very similar to MapReduce. OK, and well, in this talk, I decided to focus on distributed programming concepts because I thought that would be the most relevant for you. But I'd be happy to talk about any of these other projects in case you're interested offline. And that's all I have today. Thank you.
Okay. Chris.
Thank you.